Okay, in this video, I want to go ahead and take a look back at the different definitions that we formed and worked with in the past couple videos. We had this kind of blue, red, green, and ultimately this black title sitting down here. And we had problems that asked us, does a series absolutely converge? Does it conditionally converge? Or is it just regular old divergent? And we kind of already talked about the fact that it's totally possible, or sorry, totally impossible for a series to have the blue title and the green title at the same time. It's just not possible at all. We also looked at that it's impossible to have green and black as two titles on the same series at the same time, because the definitions just contradict each other. But there's one other pair in here that we haven't yet investigated. Can you think about what pair it is? Well, it's actually the pair of the blue title and the black title. Is it ever possible for a series to have both the blue label, converges when you put absolute value bars on it, but maybe just without absolute value bars, just as all by itself, it's regular old divergent? Could adding absolute value bars onto a series turn it from divergent to convergent? Well, if you take a look at the next page, this is what our theorem here is all about. If a series A sub n is absolutely convergent, then guaranteed it must be, with no exceptions, regular old convergent. And this is a really powerful idea. It's got to be the case that if you have the blue title, you're automatically convergent. I oftentimes will think about this theorem is kind of indicating that absolute convergence is kind of almost equivalent to like a super convergence, because if you have the blue title, you're just automatically regular convergent as well. If you're super convergent, you're certainly regular convergent. Okay? Now, of course, it might seem surprising as to how I would know that one implies the other, but we'll take a look here at a quick proof. So here's where I'll start. I'll say we note that if I was to take A sub n, the stuff that's here in this series, I can definitely claim that I know that this is going to be greater than or equal to 0 as long as I state the following. So take a look at the adjustment that I made here. I said that A sub n plus the absolute value of A sub n is definitely greater than or equal to 0. Hopefully you would agree with this, because notice if A sub n turns into the number 0, I just get 0 plus 0. If one of these values is negative, so like if A sub n is negative, then I'm going to have like negative plus the equivalent positive number, and that's going to create 0 again. And if they're both positive, well, then it's definitely bigger than 0. But in the same way, I think I can claim that this is less than double the absolute value. So this is kind of a weird spot to start, but we're going to go ahead and work with this inequality here. So here's what I'm going to suppose. Let's pretend or suppose that the series with A sub m is absolutely convergent. This is what we want to suppose, because we want to then show that if I start with this information, can I then conclude that the regular series is convergent? So we're going to suppose that the blue title applies to this series. That, of course, means that the series with absolute value bars on the A sub n converges, because that's what the blue title actually means. Okay, but then I think I could easily make the following argument. I'll say, but then, clearly, if I did 2 times this absolute value as a series, this must also converge. This is like a nice property that we had way back in 5.3.1, that you can multiply something convergent by a number and you won't change its convergence. But then notice I can do something really powerful. I can then say, since this series and the series of A sub n plus the absolute value of A sub n Notice these are exactly the pieces that we had in the original starting inequality. I have my 2 times my absolute value and my a sub n plus absolute value. And what I can see here is that since this series and this other series have only non-negative terms, which they clearly do because we said that they both those formulas only produce things 0 or larger, then by the comparison test, I can see that, wait a minute, the bigger thing up here converges, so the middle thing must also converge. So I can say that this series with the absolute value bars on that a sub n converges. But then I can go even further because I could also then use properties from 531 to say that, again, I'll say this, we then know that if I took this series, which I now know must be converging, I could go ahead and subtract from it another convergent series if I wanted to. And the series I'm going to choose to subtract is this series. Again, notice we know that one converges because the series was absolutely convergent. But you might recall that there was a cool thing that I could do when I had 2 series that were added or subtracted. As long as they were both convergent, I could kind of combine their formulas. So I could rewrite this as a sub n plus the absolute value of a sub n minus the absolute value of a sub n, which of course is just going to be equal to this series with a sub n. But I then know that this is convergent. So we've been able to say that definitely our series a sub n is regular old convergent. This is a really, really powerful fact. In fact, it's so powerful that we're going to go ahead and actually add this as kind of one of our tests in our nice little running sheet that we have sitting over here. I'll say that what we have is kind of an absolute convergence test. We know that if a series is absolutely convergent, it also must be regular convergent. So this is really, really powerful. The last thing that I'll highlight here will actually be placed down near the bottom of this page, or maybe I can squeeze it. No, I'll put it down near the bottom. I don't want to clutter number 6. But a lot of these definitions now can start to get a little bit confusing, and it can be helpful at times to kind of summarize them in the following sort of a diagram. And this diagram is really, really useful. We know that every time we come to a series, one of 2 things is going to happen. It's either going to be absolutely convergent, or it will be absolutely divergent. That is, it has a blue title or it has a red title, right? Like that's got to happen. But what we just saw up above is that whenever you are a part of the blue title, you must automatically arrive at regular old convergent. Whereas if you're absolutely divergent, one of 2 things will happen. You either get convergent or you could get divergent. So there's my black title divergent, and this convergent over here is actually our green title of conditionally convergent. This is a nice little kind of diagram to help us kind of understand all the implications. If you have the blue title, you automatically arrive at convergent. And if you have the red title, you automatically, well, don't know anything. You might converge and then get the green title, or you might diverge and just get the black title. The interesting thing, though, is that if you kind of imagine flipping this picture upside down, you could see that if I start a series with the black title, I then know immediately it does not have the blue title. If I know that something's conditionally convergent, there's no way it could have the blue title. I can see how all these things are separated out. Okay? This is a really good diagram to kind of go back to, and can really help with answering certain kinds of questions in the future when we're trying to sort through what all these different definitions actually mean. Okay, in the next video, I'm going to take a look here at example number 6 and see us actually try to put to use this new powerful theorem.